Hi, today I want to show you this PCB that I made. It's a buck boost converter that we can control with I2C, which means we can use any MCU to change the voltage output and other settings. It's based on the LM51772 buck boost controller. And if you are not new to my channel, you know I've already built an I2C controllable buck boost converter in the past with the TPS55289. That is a converter IC. Whereas the LM51772 is a controller IC. What's the difference? Well, a converter has integrated MOSFETs, whereas a controller has not. So you have to implement them externally. But this time we have a larger voltage range on both input and output. Anyway, why do we want an I2C controllable buck boost converter in the first place? Well, because we want to change the output voltage without physically turning the potentiometer. And the LM51772 can do this and many more things. By the way guys, if you want to support me, you can leave a like and subscribe. Okay, now let's quickly see the PCB. Here there is the input, and those 4 holes are for a screw terminal that I've not mounted yet. This one. And then of course we have the input capacitor here. Then we have the 8 MOSFET here, the main inductor, the output capacitor, and then the output screw terminal. At the top here we have adders for voltage sensing and other adders for other stuff, for example the I2C interface. Then we have the frequency dip switches here with the various frequencies. Then there is a DC bias switch, an I2C address selection switch, a reset for the main core logic, and the enable for the buck boost stage. Now as you can see, this PCB is way bigger than the other I made, but this one is more an evaluation board rather than a ready-to-go module. But you could of course use smaller components, have higher switching frequency for overall smaller size. And if you're interested in designing with this IC, Texas Instruments has also an evaluation board that you can check. This one is surely done better than mine, and you can also check their schematic and PCB layout. To help me test this board, I've prepared a custom interface with this Arduino Mega and a TFT display. Now let me plug it in. There we go. This is the interface. And if I click here at the bottom, something interesting will happen. PCBWay could be the sponsor of this video. If you want really good looking PCB, I highly suggest to check PCBWay.com using the link in the description. They can also assemble PCBs for you or offer 3D printing and CNC machining, with tons of material to choose with. Just check PCBWay.com, link in the description. Okay guys, I have here my custom interface. I have the PCB here, I have the multimeter and an LED to check the status of the buck boost converter. Now I turn on the power supply and also the PCB, both the core logic and the buck boost stage. And finally we want to power up our custom interface here. So let's plug it in. And there we go, you see the LED lights on and we have our interface. Now the converter is off, 0 volts, and now we click enable and let's go. There we go, 12 volts on our output, which is the standard initial value. You can also see the LED turn on. And now we're gonna modify the voltage. This is the voltage menu. And here at the top you have the various voltages, for example 3.3 volt, 5 volt, 9 volt, 12 volt, like the most common voltages. Let's go to 3.3. Now 5 volt. There we go, precise 5 volt. Again 9 volt, a precise 9 volt, 12 volt. See, it's always super precise. 24 volt. See, and then 48 volt. There we go. And this is the maximum voltage we can get with I2C. Now let's go back to 5 volts And I'm going to show you that we can modulate it in 10 millivolt steps. See? 4.99, 98, 97. Of course, 100 millivolt works well. There we go, 5.07, 5.17, 1 volt. There we go, 6.16. And you will have 10 millivolt steps up to 24 volt. After that, your minimum step will be 20 millivolt, which is still pretty dang good for that kind of range. Now I can also type in a custom voltage, for example 12.3 volt. There we go, precise 12.3 volt. Let's try again, this time with 34.88. Let's try. There we go, super precise as you can see. Now let's go back to a lower voltage, so we clear here and we do, for example, 12.71. Okay, still pretty accurate, you can see. And what else? Well, let's subtract, for example, 1 volt to see if it works. But of course it works. Now let's go to 5 volts and let's see the minimum voltage we can get. See, 3 volt, 2 volt, 1 volt. See, we can go as low as 1 volt. The minimum here is, yeah, a precise 1 volt, as you can see. Okay, now I'm back here on the main menu. We disable the converter, and as you can see, the voltage will drop down. Now let's go to the current menu, where we can set the current mode for this buck boost converter. The standard is 1000 milliamp. Now let's go a little bit up, for example 1.5 amp. That's okay. We enter and then we enable the control current. Okay, now let's speed up a little bit the video. You know guys, what's the best resistor here? This Chinese cables. Perfect for power resistors because they are trash, but we can use it as power resistors. Well, I mean, I guess. Well, maybe they are trash even at this. Anyways, now let's connect to the output. There we go, connected. Okay, now we can enable our buck boost converter again, but first let's go to 5 volt. There we go, 5 volt, LED lit on, current mode, 1.5 amp as before. Now let's connect the other end, and there we go, the voltage drop. Of course, even here I can lower the current if I want. So see, at 1.3 amp we have only 3.8 volt, and as I lower the current, the voltage also lowers. Well, we can also of course add it in 500 milliamp steps. There we go, and now we have the full voltage. Now the way this works is your converter checks the voltage drop on your sensor resistors, and it will limit it to a fixed value that you can set through I2C. The minimum step we can have for 10 milliohm is 50 milliamp. So for 5 milliohm that I have is 100 milliamp. Okay, now next feature. I disable the converter and remove the cables because I want to show to you another great feature, that is the cable drop compensation, or CDC. What it does is, well, you know when you have really long cables and if you put too much current, the voltage drops too much. Well, CDC tries to compensate for that voltage drop. And the voltage you see written under CDC is the voltage gained per amp. Okay, to help me test the CDC mode, I have here my electronic load. Now let me lower the current. We can enable the converter. As you can see, we have 5 volt. Okay, now let me move a little bit the camera here. Okay, now the compensation is of 25 millivolt. Let's go to 100 millivolt. So every amp we add the 100 millivolt. And since on the converter we have 500 milliamp, we should expect a rise of 50 millivolt. So let's enable the compensation and also the electronic load. See, the voltage is rising as expected. Now if we add current, of course also the voltage adds up. 1 amp is 100 millivolt, as you can see in here. Of course, if we turn off the electronic load, we return to the initial value. Now let me use a higher voltage gain, for example 200 millivolt, and now to get the same voltage as before, that was 5.1 volt, we only need half the current, so 500 milliamp. Now if we start the electronic load, we see we get the same voltage as before with half the current. And if we rise to 1 amp, we get, of course, double the gain. If you have long cables, this is a perfect feature for you. Now we also have 25 millivolt and 50 millivolt gain if I want. Now let me disable the CDC and see how this works. As before, the converter senses the voltage drop on your sense resistor. It then multiplies it by the transconductance of the CDC stage, and then it multiplies it by the CDC resistance. Now this is the voltage in your CDC pin. Then we can select the gain through I2C that will lead to the final voltage that we had. Here I show to you an example, so hopefully you will understand better. Okay, now we disable the converter to show to you another great feature. You can see now the voltage is going down, and if we click discharge, well, it discharges to alpha volt. This is a really cool feature if you don't want your capacitor to hold the voltage while the converter is off. Now the converter also has a special pin called the drive pin, which here on the schematics drives an N-channel MOSFET for reverse polarity protection, whereas I use it only to lit an LED. Now you can see if the DRV is on, the dcdc is on. So let's try it. Now if we enable the converter, you can see the LED is on. Okay, see? And if we disable it, of course it goes off. We can also force the DRV pin to be always on. As you can see, now it will be always on regardless of the state of the converter, or always off, of course. If we need it, it will be always off. See? And also we have the complementary of the first mode, so it will be on when it's off, I will be off when it's on. See? And you can also have other 4 configuration for your DRV pin that will not affect the on or off status, but rather the implementation of your DRV pin. Okay guys, now I'm gonna show you the last feature, which is the input voltage detection function. As you can see, we have the fall and rise threshold here, and if I update the fall, for example, let's do 5.3 volt, there we go. The rise, instead we go a little bit higher. We have to be higher, of course, 6.2 volt. We can update the rise and update the fall threshold voltages. And now as you can see, I have 15 volt at the input. The converter is off, so we enable it. Okay, we have 5 volt, as you can see it's on. Let me go to the input voltage detection menu. Okay, there we have it. So if I go down with the voltage, we go to 6 volt. You can see it's still operating because the falling threshold is 5.3 volt. So if you go to 5 volt, you can see the voltage is going down, so the converter is off. Now if I raise it to for example 3.4 volt, it still doesn't turn on because the rise threshold is 6.2 volt, so I have to be higher than that. so for example 7.4, and then we have it back it running. The converter has many more features you can tweak through I2C for even more customization. Now if you want to start designing with this IC, I'll suggest to check the evaluation board made by Texas Instrument. They also provide schematics and PCB layout. They also provide a guide for that evaluation board where you can find even the bill of material. You can also, of course, want to check the datasheet of the converter itself. Two more tools are the Vbench tool, and there is also an Excel file that you can check called the Quick Start Calculator tool for the LM51772. Okay guys, the video ends here. Tell me what you think, subscribe, and see you next time. Bye.